Welcome! In this video, we'll tackle LeetCode problem number 411, minimum unique word abbreviation. This is a challenging yet fascinating problem that combines string manipulation and bit masking techniques to find the smallest unique abbreviation for a given target string. Let's dive into the problem and explore how we can solve it step by step. In this problem, you're tasked with finding the minimum unique abbreviation of a given target string. The target string consists of lowercase English letters, and you're also provided with a dictionary, which is a list of other strings. The goal is to abbreviate the target string in such a way that the abbreviation is not a substring of any word in the dictionary. An abbreviation is created by replacing consecutive characters in the string with their count. For example, the word apple can be abbreviated as F4, where the pli is replaced by its length, or 5, where the entire word is replaced by its length. Other examples include AP3, AP2, and so on. The challenge lies in finding the shortest possible abbreviation that meets these criteria. If there are multiple abbreviations of the same length, you should return the lexicographically smallest one. The output of the problem is a string that represents the minimum unique abbreviation of the target string. Let's consider an example. If the target string is apple and the dictionary contains the word blade, the output would be A4. Here, the abbreviation A4 is valid because it does not appear as a substring in blade. Other possible abbreviations of apple, like AP3 or 5, either don't meet the uniqueness condition or are longer than A4. Therefore, A4 is both unique and the shortest abbreviation in this case. In another example, if the target string is again apple but the dictionary contains the words plain, amber, and blade, the output would be 5. In this case, the abbreviation 5 is unique because it does not appear as a substring in any of the dictionary words. While abbreviations like A4 or AP3 are also valid, 5 is the shortest. So, among all possible abbreviations, 5 is the one that satisfies the conditions of being unique and having the minimum length. There are a few constraints and edge cases to keep in mind. First, the length of the target string can range from 1 to 21, and the dictionary can contain up to 100 words. Each word in the dictionary will always have the same length as the target string. All strings, whether in the target or the dictionary, consist solely of lowercase English letters. For edge cases, if the dictionary is empty, the shortest abbreviation is simply the length of the target string, represented as a number. On the other hand, if no valid abbreviation satisfies the uniqueness condition, you return the target string's full length as its abbreviation. Finally, when multiple abbreviations of the same length are possible, always choose the one with the smallest lexicographic order. To tackle the minimum unique word abbreviation problem, our goal is to find the shortest abbreviation of the target string that does not conflict with any word in the dictionary. The challenge lies in balancing two competing objectives, minimizing the abbreviation length while ensuring it remains unique compared to the dictionary. One approach is brute force. Here, we would generate every possible abbreviation of the target string by replacing characters with wildcards. For instance, the string ABCDA could be abbreviated as 3A1, where 3 represents 3 wildcard characters. After generating the abbreviations, we would check each one against the dictionary to ensure no conflicts, and finally return the shortest valid abbreviation. However, this method has significant trade-offs. Generating all possible abbreviations results in exponential growth, requiring 2 to the power of L, time for a target of length L. On top of this, checking each abbreviation against the dictionary further amplifies the complexity to 2 to the power of L times N times L, where N is the dictionary size. While this approach guarantees correctness, it becomes impractical for longer strings due to its computational expense. Thus, it is only feasible for very small inputs. To improve upon brute force, we can use an optimized backtracking approach combined with bit masking. The key intuition here is to represent abbreviations as binary bit masks, where a 1 keeps the character and a 0 replaces it with a wildcard. This drastically reduces the search space while enabling efficient conflict checks. The first step in this approach is to pre-process the dictionary, filtering out words whose lengths don't match the target, as they cannot conflict structurally. Next, we use bit masks to systematically generate abbreviations while prioritizing shorter ones to minimize length. Backtracking ensures that we explore all promising candidates without unnecessary computations. For each abbreviation, we use bitwise operations to quickly determine if it conflicts with any dictionary word. Once a valid abbreviation is found, we return it. By leveraging bitmasking and backtracking, we achieve a significant reduction in complexity, down to 2 to the power of L plus n times L. This approach is far more efficient than brute force while still guaranteeing correctness. The main trade-off lies in the complexity of implementing bitmasking and the need for precise backtracking logic. Another approach we considered is a greedy strategy with pruning. This method uses a heuristic to generate abbreviations in a step-by-step manner. It starts with the shortest possible abbreviations, progressively increasing their length only as needed. At each step, we check for conflicts with the dictionary, and the process stops as soon as a valid abbreviation is found. The advantage of this method is its speed, with typical complexity around O and *L, depending on the heuristic used. However, it comes with trade-offs. While faster, this approach sacrifices robustness, as the heuristic may overlook the optimal solution. After evaluating these methods, the optimized backtracking with bitmasking approach was chosen for its balance of efficiency, correctness, and scalability. By representing abbreviations as bitmasks, we avoid the exponential blowup of brute force and ensure accuracy compared to the less reliable greedy approach. The critical insight here is that binary representations allow us to operate directly on the structure of abbreviations, making this method both practical and elegant. To summarize the trade-offs, the brute force approach guarantees correctness but is computationally infeasible for longer strings due to its exponential complexity. On the other hand, the greedy approach is faster but lacks robustness, as it does not guarantee finding the shortest valid abbreviation. The optimized backtracking with bitmasking method strikes the ideal balance, offering efficiency without compromising accuracy. This makes it the most practical choice for solving the problem, especially for moderate-length strings in dictionaries. In conclusion, by combining bitmasking to reduce the search space with backtracking to prioritize shorter abbreviations, this strategy achieves both performance and correctness. It effectively addresses the challenges of the problem, making it a compelling and scalable solution. In this problem, we aim to find the smallest abbreviation of a given target string such that it does not overlap with any word in the provided dictionary. Abbreviating a word involves replacing sequences of consecutive characters with their length. For example, the word can be abbreviated as W2D by replacing the middle two characters with their count. The challenge is to minimize the abbreviation's length while ensuring it remains unique when compared to the dictionary. The algorithm begins with pre-processing, where we filter the dictionary to retain only the words that are the same length as the target. This step is crucial because abbreviations of the target only conflict with words of the same length. Additionally, we compute a bitmask representation for each word. A bitmask allows us to match the structure of an abbreviation with the positions of preserved characters in the target. Next, we generate all possible abbreviations for the target string using bitmasks. For a target of length n, there are 2 to the power of n possible bitmask combinations. Each bitmask directly translates into an abbreviation. For instance, the bitmask 1011 4-word results in W2D. The length of each abbreviation is then calculated based on the bitmask, setting the stage for selecting the shortest valid one. To ensure efficiency, all generated abbreviations are sorted by their length, with shorter abbreviations prioritized. This allows us to focus on minimizing the length of the abbreviation. Once sorted, the algorithm validates each abbreviation by checking its uniqueness against the dictionary. This validation step compares the abbreviation's bitmask to the bitmasks of words in the dictionary. If no conflicts are found, the abbreviation is considered valid. At this point, we can immediately return the smallest valid abbreviation, as the sorting ensures that we encounter the shortest one first. This approach allows the algorithm to terminate early, avoiding unnecessary computation on longer abbreviations once the optimal solution is identified. A few key insights help make this algorithm both efficient and effective. First, the bitmask representation is central to the process. It provides a compact way to determine which characters in the target string are preserved or replaced by numbers. For example, a bitmask of 1011 for the target word results in the abbreviation W2D. By sorting abbreviations by their length, we ensure that shorter abbreviations are prioritized, reducing the need to explore longer, less optimal options. Pre-processing the dictionary to include only words of the same length as the target significantly reduces the number of comparisons required, as shorter or longer words cannot conflict with the target's abbreviations. Finally, the algorithm leverages early termination, halting as soon as the smallest valid abbreviation is found. This avoids unnecessary exploration and ensures the process is computationally efficient. In terms of data structures, bit masks are used to represent preserved character positions, heaps or sorted lists facilitate efficient access to the shortest abbreviations, and sets provide quick checks for conflicting bit masks in the dictionary. Analyzing the algorithm's complexity, we see that generating all possible abbreviations involves 2 to the power of n operations, where n is the length of the target string. Validating each abbreviation against the dictionary requires m comparisons, where m is the size of the filtered dictionary. Additionally, sorting the abbreviations contributes a complexity of O(2 to the power of n asterisk log, 2 to the power of n). Combining these factors, the overall time complexity is O(2 to the power of n asterisk log, 2 to the power of n plus m. For space complexity, storing all 2 to the power of n abbreviations requires O(2 to the power of n space. The algorithm also handles several edge cases. If the dictionary is empty, the smallest abbreviation is simply the length of the target. If the target is empty, the result is an empty abbreviation. Finally, in scenarios where every word in the dictionary conflicts with the target, the algorithm defaults to returning the target itself, as no abbreviation would be valid in this case. To tackle the problem of finding the minimum unique word abbreviation, we start by importing the product function from the itertools module, which will help us generate all possible combinations of binary bit masks. Next, we define the min-abbreviation method within the solution class. The first step in this method is to filter the dictionary to only include words with the same length as the target word. This is because only words of the same length could potentially conflict with the abbreviation of the target. If no words remain in the filtered dictionary, we can directly return the length of the target word as its abbreviation, since there are no conflicting abbreviations to consider. To explore all possible abbreviations, we generate bit masks that represent which characters in the target word will be abbreviated. To do this, we define a helper function generate_masks that uses product to yield all combinations of zeros and ones for the length of the target word. Additionally, we define another helper function, abbreviation_length, which calculates the effective length of an abbreviation generated by a specific bit mask. This function iterates through the mask, counting consecutive abbreviated characters and adding their contribution to the length, while also counting non-abbreviated characters. This gives us the ability to rank bit masks based on their abbreviation length, which will be useful later when searching for the optimal solution. Now, we define the function generate_abbreviation, which creates the actual abbreviated string for a given bit mask. For each bit in the mask, if it is set to 1, we count how many consecutive characters are being abbreviated. When we encounter a 0, meaning the character is not abbreviated, we append the count, if any, to the abbreviation, followed by the actual character from the target word. At the end, if there is a remaining count of abbreviated characters, we append it as well. This function ensures that the generated abbreviation matches the rules of the problem. Next, we implement the is_unique function, which checks if an abbreviation generated by a given bitmask is unique with respect to all words in the filtered dictionary. For each word in the dictionary, we verify whether the abbreviation conflicts by ensuring that either the bitmask allows abbreviation at a position or the characters of the target and the dictionary word match exactly at that position. If any word leads to a conflict, the mask is deemed invalid. Finally, we generate all possible bitmasks using the generate_masks function and sort them based on their abbreviation length, using the abbreviation_length function as the key. This ensures that we evaluate shorter abbreviations first. We iterate over the sorted bitmasks, checking each one for uniqueness using the is_unique function. If a valid mask is found, we return its corresponding abbreviation generated by the generate_abbreviation function. If no valid bitmask is found during the iteration, the method returns an empty string as a fallback. However, this scenario is highly unlikely to occur, given that the problem guarantees the presence of a solution. This concludes the implementation of the min-abbreviation function, which systematically explores all possible abbreviations, prioritizing the shortest ones, and ensures that the chosen abbreviation does not conflict with any word in the dictionary. Here, we begin by importing the necessary libraries and setting up the main function to find the minimum unique word abbreviation. The first step is to identify words in the dictionary that have the same length as the target word, since only those can conflict with our abbreviation. We filter the dictionary accordingly and store these matching length words in a list called filtered dict. If there are no such words, we can simply abbreviate the target word by its length, as there are no potential conflicts. Next, we generate all possible bit masks representing different abbreviation patterns for the target word. These bit masks will later help us form and evaluate potential abbreviations. The bit masks are then sorted based on the abbreviation length they produce, ensuring that we prioritize shorter abbreviations. Finally, we iterate over these masks to find the first abbreviation that is unique, meaning it does not conflict with any word in the filtered dictionary. If a unique abbreviation is found, we return it. In this part of the implementation, we handle the continuation of the abbreviation generation process. If a unique abbreviation is identified, we use the generateAbbreviation function to create the corresponding string and return it. If no unique abbreviation is found, which is highly unlikely, we fall back to returning an empty string as a safeguard. Moving on, the generateMasks helper function is defined to create all possible bit masks for the target word. These bit masks are binary representations where each bit indicates whether a character in the target word should be included as is, 0, or replaced by a number in the abbreviation, 1. To achieve this, we utilize a nested loop. The outer loop iterates through all potential mask combinations from 0 to 2 to the power of n1, where n is the length of the target word. The inner loop converts each integer into its binary representation and populates the mask array. Once all masks are generated, they are returned as a list. Additionally, the calculateAbbr function is introduced to compute the effective length of an abbreviation for a given mask. This function plays a crucial role in sorting the bit masks by abbreviation length. Here, we continue with the calculateAbbr function, which determines how long an abbreviation would be based on the bit mask applied to the target word. The function iterates over the mask array and calculates the total length of the abbreviation. If a sequence of consecutive ones is encountered in the mask, it represents a number in the abbreviation, which contributes 1 unit of length. Meanwhile, each 0 in the mask corresponds to retaining the original character, which also adds 1 unit of length. The logic ensures that trailing numbers are properly accounted for by checking if there are any remaining counts after the loop. Once the length calculation is complete, the function returns the computed value. Next, we have the generateAbbreviation function, which constructs the actual abbreviation string based on the given mask and target word. Using a string builder for efficient string manipulation, the function iterates through the mask. When encountering a sequence of ones, it appends the count of consecutive ones as a number in the abbreviation. For zeros, it directly appends the corresponding character from the target word. This process continues until the abbreviation is fully constructed. Finally, the generateAbbreviation function handles any trailing sequences of ones by appending the final count to the abbreviation. The completed abbreviation string is then returned. The last helper function, isUnique, is responsible for verifying if a given abbreviation, determined by the mask, is unique against the filtered dictionary. It does this by iterating through each word in the dictionary and checking character by character whether the abbreviation conflicts with the word. For each bit in the mask, if the bit is 0, the corresponding character in the target word and the dictionary word must match. If any mismatch is found, we can immediately conclude that the abbreviation does not conflict with that word. However, if all characters satisfy this condition, the abbreviation is deemed non-unique, and the function returns false. If no conflicts are found with any word in the dictionary, the abbreviation is confirmed to be unique, and the function returns true. This ensures that the generated abbreviation is both minimal and valid. To solve the problem, we begin with pre-processing. Our target word is apple, and the dictionary contains one word, blade. The first step is to filter the dictionary to only include words that are the same length as the target. Since blade has the same length as apple, it remains in the filtered dictionary. Next, we generate all possible bit masks for the target word. A bit mask is a combination of zeros and ones, where each bit represents whether to keep or abbreviate a character in the target. For a word of length 5, such as apple, there are 2 to the power of 5 or 32 possible bit masks. For example, the bit mask 00000 means no characters are abbreviated, while 11111 means every character is abbreviated. These bit masks serve as the foundation for generating potential abbreviations. Next, the generated bit masks are sorted based on the length of their corresponding abbreviations. The abbreviation length is calculated using the abbreviation_length function, which considers the number of characters kept in the groups of abbreviated characters. For instance, the bit mask 00110 results in the abbreviation AP2E, which has a length of 4. On the other hand, the bit mask 11111 produces 5, which has a length of 1. By sorting the bit masks in ascending order of abbreviation length, we prioritize shorter abbreviations. After sorting, we check each mask for uniqueness using the is_unique function. This function ensures that the generated abbreviation does not conflict with any word in the filtered dictionary. For example, the abbreviation 5 from the mask 11111 conflicts with blade because it completely abbreviates the target, making it indistinguishable. However, the abbreviation AP2E from the mask 00110 does not conflict with blade, making it valid. Thus, AP2E becomes our minimum unique abbreviation. Now let's consider another example with the target word hello and a dictionary containing hello and hello. First, we pre-process the input by filtering the dictionary to include only words of the same length as the target. Both hello and hello match the length of hello, so they remain in the filtered dictionary. Next, we generate all possible bit masks for the target, which again results in 2 to the power of 5 or 32 combinations. After generating the bit masks, we sort them by the length of the abbreviations they produce. For instance, the mask 11111 generates the abbreviation 5, while the mask 01010 produces H2L2. Finally, we check each mask for uniqueness. The abbreviation 5 conflicts with both hello and hello because it fully abbreviates the target, making it indistinguishable. However, H2L2 does not conflict with any word in the dictionary, making it a valid abbreviation. Therefore, H2L2 is the minimum unique abbreviation for this example. In the final example, the target word is word, and the dictionary is empty. Without any dictionary words, there are no potential conflicts. During pre-processing, no filtering is needed since the dictionary is already empty. Since there are no conflicting words, the entire target word can be abbreviated. The output in this case is simply 4, which represents the length of the target. To summarize the key takeaways, first, we generate all possible bit masks for abbreviation, which results in 2 to the power of n combinations. Second, we sort these bit masks by the length of their abbreviations to prioritize shorter ones. Third, we ensure that the abbreviations are unique by checking for conflicts with dictionary words. Finally, we return the first valid abbreviation as the result. This approach ensures that we find the shortest unique abbreviation efficiently. To analyze the time complexity of this algorithm, we start by breaking it into its core components. The first step is filtering the dictionary. Here, we compare the lengths of all words in the dictionary to the target word's length. If the dictionary contains m words and the target word has a length of n, this comparison requires m*n operations. Next, we generate all possible bit masks of length n. Since there are 2 to the power of n possible bit masks for a word of length n, this step takes 2 to the power of n time. These 2 steps form the foundation of our algorithm's complexity up to this point. Now, we move to sorting the bit masks based on their abbreviation lengths. For each bit mask, the abbreviation length is computed by iterating over its n bits. This computation takes n per bit mask. With 2 to the power of n bit masks, the sorting process requires 2 to the power of n*n for computing lengths, along with a sorting overhead of 2 to the power of n** log 2 to the power of n. However, the length calculation dominates, so this step simplifies to 2 to the power of n*n. The next crucial step is checking the uniqueness of each bit mask. For a given bit mask, we compare it against all m words in the dictionary, requiring m*n per mask. Since there are 2 to the power of n bit masks, the uniqueness checks contribute 2 to the power of n times m times n to the overall complexity. Finally, if a unique bit mask is found, generating the corresponding abbreviation involves iterating over the n bits, which takes n. Since this occurs only once, its impact on the overall time complexity is minimal. Considering all these steps together, the overall time complexity is dominated by the uniqueness checks, resulting in 2 to the power of n times m times n in the worst case. In the best case, if the first mask evaluated is unique, the algorithm terminates early. Here, the time complexity reduces to 2 to the power of n*n for mask generation and sorting, plus m*n for a single uniqueness check. However, in average and worst case scenarios, the term 2 to the power of n times m times n dominates. Shifting to space complexity, we start with the storage of bit masks. With up to 2 to the power of n bit masks, each of size n, the total space required is 2 to the power of n*n. Additionally, the filtered dictionary requires storage for up to m words of length n, contributing m*n to the space complexity. We also need to account for auxiliary space used during the algorithm. Temporary variables, such as those for masks, abbreviations, and counters, require n space. Sorting introduces additional overhead proportional to the number of masks, which is 2 to the power of n. Combining these factors, the overall space complexity is dominated by the storage of bit masks, resulting in 2 to the power of n*n. Secondary contributions, such as dictionary storage, lead to a total space complexity of 2 to the power of n times n plus m times n. Even in the best-case scenario, where early termination occurs, the need to generate and store all bit masks ensures that the space complexity remains 2 to the power of n*n. To understand the improvement of this algorithm, we compare it to a brute force approach. A naive solution would generate all possible abbreviations of the target string by examining all substrings and combinations. This results in exponential growth, requiring 3 to the power of n abbreviations, where 3 to the power of n accounts for each character being kept, replaced by a number, or skipped entirely. Each abbreviation would then be checked for uniqueness against the dictionary, requiring m*n per check. Combining these steps, the brute force method has a time complexity of 3 to the power of n times m times n. By leveraging bit masks, our algorithm reduces the search space, achieving a time complexity of 2 to the power of n times m times n. This improvement is rooted in the mathematical observation that the algorithm evaluates all 2 to the power of n bit masks and performs m*n operations per mask. The filtering and abbreviation length calculations are secondary in impact, as their contributions are dominated by the uniqueness checks, solidifying the overall complexity at 2 to the power of n times m times n. When solving this problem, there are several common mistakes to watch out for. First, not accounting for dictionary constraints can be a major pitfall. The abbreviation you generate must not be a substring of any word in the given dictionary, so it's important to validate each abbreviation thoroughly. Another frequent issue is relying on inefficient brute force approaches. Generating all possible abbreviations and filtering them one by one can quickly lead to time limit exceeded errors. Instead, leveraging bit masking allows you to systematically and efficiently generate abbreviations. Edge cases are another area where mistakes often occur. Scenarios like an empty dictionary, a single character target, or cases where the target word is already unique need special attention, as missing these can result in incorrect outputs. Additionally, some solutions fail to correctly calculate the length of an abbreviation, especially when it includes numbers representing character groups. For example, A2C4ABC should be counted as length 3, but errors here can lead to invalid results. Lastly, skipping pruning during DFS or backtracking is another key mistake. If you don't terminate invalid paths early, you'll waste time on unnecessary computations, so effective pruning is essential to improving efficiency. Now, let's consider some insights that are particularly useful in an interview setting. The core of this problem lies in balancing two objectives: minimizing the length of the abbreviation while ensuring it doesn't conflict with the dictionary. Efficiently generating abbreviations, such as through bit masking and pruning invalid candidates, are critical to achieving this balance. This problem is also a great showcase of algorithmic thinking, as it combines techniques like bit manipulation, backtracking, and optimization. Interviewers may ask about trade-offs between approaches. For instance, while brute force or BFS might work for small inputs, they are less efficient for larger cases, and you should be ready to explain why more optimized methods are preferable. Additionally, you'll want to analyze the time complexity of your solution. A common efficient approach has a complexity of O2 to the power of n asterisk k, where n is the length of the target and k is the size of the dictionary. Being able to articulate this clearly can demonstrate your understanding of the problem's computational challenges. It's helpful to explore related problems that share similar concepts or techniques. For example, LeetCode 320, Generalized Abbreviation, focuses on generating all possible abbreviations for a given string, which is fundamental to this problem as well. LeetCode 212, Word Search 2, emphasizes handling dictionary-based constraints, which is another critical aspect here. Meanwhile, LeetCode 52, nqueens 2, and its more general version, LeetCode 51, nqueens, involve pruning invalid configurations during backtracking. These problems are excellent practice for honing your ability to systematically explore possibilities while efficiently ruling out invalid options. By studying these related problems, you can strengthen your understanding of the techniques needed for this challenge, such as backtracking, pruning, and efficient constraint management. Finally, let's discuss some alternative approaches and their trade-offs. Brute force, while conceptually simple, involves generating all possible abbreviations and filtering them against the dictionary. This approach is computationally expensive, with a complexity of O2 to the power of n asterisk k, and is only suitable for very small inputs. A more efficient method is bit masking, which treats each bit as an indicator of whether to abbreviate a character. This reduces redundant computations and speeds up the process significantly. Backtracking with pruning is another powerful approach. It allows you to systematically explore potential abbreviations while terminating invalid paths early, striking a balance between clarity and performance. BFS and DFS can also be employed to explore all abbreviation possibilities, and when combined with memoization, they help avoid redundant calculations. Each of these methods has its strengths, and understanding when to use them is key to tackling this problem effectively. Great work! We've successfully tackled LeetCode problem number 411, using concepts like bit masking and backtracking to solve the challenge. Remember, this problem is a great example of how to combine creativity and efficiency in algorithm design. Don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!